Yeah, thank you for this warm welcome. Can I get a show of hands who has played Horizon Forbidden West? Oh, wow, that's like more than half of the room. That's super cool. And how many of you worked with flying or swimming NPCs? That's also quite substantial, like 30, 40%? That's cool. I'm curious to hear maybe later of what your situations is and what challenges you face. My journey in game dev actually started in working in casual mobile games at a studio called Booger. I was working on a game called Futurama Game of Thrones and some other casual matching games. So I was actually quite excited to see a talk here today about casual matching games and game AI in this. Back then I was really excited about game AI, and I attended a lot of conferences very similar to this one to learn more about this, and was actively looking for opportunities to work on this stuff. Unfortunately, the possibilities to apply this to casual matching games were quite limited at that time, and also just due to the constraints and size of projects. So eventually, I decided to go back to university and study a master's in artificial intelligence, which was a lot more about machine learning and its general applications to all sorts of problems, and had very little to do with games. It was quite interesting, but I was really missing to work on games, and particular NPC behavior using more the good old-fashioned kind of tech. So I was very excited when I got the opportunity to join Guerrilla for the development of Horizon Forbidden West in 2020 on the AI team, and gradually worked with various NPCs and the tech that we developed there. And over time, worked more and more with flying machines. And for the DLC, The Burning Shores, I was the main responsible AI programmer for the new flying machine, the Waterwing, introduced in the DLC. Now, to make sure that you all have an idea of like what our game is like and what our machines look like and the encounters, I have a trailer to give you an impression.
The land is dying, and the machines are out of control. Whatever comes, I will be ready.
For this talk, I want to specifically focus on one of our machines, the Waterwing, partially because it's actually the only machine who can fly and swim at the same time, but also focusing on one particular machine helps to give the talk a bit of more structure and to illustrate the various components. All the components I'm presenting here today, they're way more general than only for the Waterwing, and we use them on all our flying and swimming machines, which are often mutually exclusive. When it comes to building a new machine from the AI side perspective, we do start with a briefing from design. And from the Waterwing design document, I got this paragraph, which states, "The Waterwing is a tough, semi-aquatic flying robot that uses land-based resources to create algae bloom underwater. It is extremely aggressive, works in groups, and it's very dangerous when confronted, focusing on relentless melee attacks during combat." Now, there's a lot of information in this paragraph, and it actually describes more than I can go over in this talk. But I want to focus on two particular aspects as two parts of this talk. First, talking about the promise of the title of how do we actually build a semi-aquatic flying robot, so a robot that can swim and fly. And then there will be a second part where I want to talk a little bit on how we use melee attacks in Horizon Forbidden West, and how does this relate to being underwater or being in the air. what does the melee attack mean for this? For completeness sake, I wanted to mention that our decision system that we're using is called Hierarchical Task Network, or HTN. My colleague Tim gave an in-depth talk about this already earlier today, and if you haven't catched it, I highly recommend watch this recording. The things I'm talking about, showing in this presentation, they're fairly independent of what kind of decision logic you're using, and they're additive to this. So whatever you're using for your game, all of the things I'm presenting should still play. So in the first part, we're going to see the flying and components that allow us to fly and swim. And as a little teaser, at the end of this segment, I want to show you the Waterwing's idle behavior, which takes all of these components together and takes then resources from the land, flies into the sky, finds some place in the water to spread these algae blooms that you can see here in this screenshot. Now, for the start, we start out somewhere on the ground. We do have nav mesh, like most games these days, to allow us to reason about where we can go on there. And to introduce some terminology, we have a component we call mover that handles steering and clamping to the navigation structure in this particular medium. So we have a ground mover that makes sure we stay on the nav mesh, we can move around with this, we drive the animation necessary for the locomotion, etc. To fly now, we first need to take off. We need to get off the ground. But wait, before we just jump up in the air and flap our wings, we need to make sure that wherever we're taking off is actually a sensible space. So if it's a small room and there's a roof over us, we don't want to crash into the room. Or if there are some other issues that prevent us, like our wings are broken because the player destroyed the components on them or something like this. Once we know that takeoff is valid, we'll play a takeoff animation. And the movement during a takeoff is completely animation driven at that part. We will, during the animation, disable nav mesh clamping. Not right at the start, because as you can see here in this animation, during many takeoffs, we have a few steps or jumps at the beginning where we still move on the nav mesh, and we don't want our machines to jump over a cliff at this point and walk in the air. That would look quite silly. So we still have nav mesh clamping enabled until a certain animation event tells us now it's time to turn it off. Then, based on another animation event, we're going to switch movers. So we switch to a different component that allows us to steer the machine in the air. And I will tell in more detail about how this works in a bit. And lastly, once this animation finishes, we finish this transition and we're officially in the air now. Just to make sure that this is not a one-way street, let's have a brief look at landing. Very similarly, we need to make sure that our destination is sane. In this case, it's some point on the nav mesh from where we then can continue navigating. It's, again, animation driven, so we play the landing animation. We'll have to disable our clamping against our air navigation structure called SVO, and I'll explain more about this after talking about the mover. And we'll switch back to the ground mover to regain our ability to steer on the nav mesh. And again, this transition finishes as soon as the animation finishes. Now, when it comes to movement in the air, we have a big advantage compared to moving on the ground. And that is, we don't have constant contact with geometry. One big challenge by moving on the ground is that you want to provide foot sliding, and you can't just programmatically, at least not easily, move your character from code. You need to make sure that the animations kind of matches. In the air, we don't have that problem as much, because you don't have the contact, but also humans are not that good to associate wing flaps with how you're supposed to move in the air. So we basically get away with relatively simple particle physics simulation, where we just, on our agent, have a certain velocity, and at each simulation step, we displace it along the velocity. And if you want to change directions, we don't directly set a velocity, but instead we apply an acceleration into the desired direction we want to go, and velocity then gets gradually updated. One thing to note here is we have a similar simulation running independently for our turn direction. So we have a turn velocity and turn acceleration, controlling in which direction we're facing. And the reason for this is that in the air, we have two different movement modes. The first movement mode we call hover, and you can think of this like a helicopter. It allows us to stay in the middle of the air on the spot, rotate on the spot like a helicopter or a tank, if you like. And it also allows us to move in the air by facing a completely separate direction. So basically do strafing maneuvers like you can see in this video clip. And they are particularly useful in combat situations where you maybe want to fire a projectile at the player while being more difficult to aim at it yourself. Also for investigation and search, if you lost the player and just want to look around where they might be. And our second movement mode is called glide. This one, you can think of the movement of an airplane. So here, the direction we're facing and the direction we're moving is aligned. And we're moving in the same direction as we're looking. And we're not allowed to stop while gliding. If you want to stop, you actually have to transition to hovering again. And the main importance of gliding for us is that our machines, they're very much inspired by nature, by animals. And to sell this animal inspiration, we want them to look like a flying bird. And most birds move around with more glide-like maneuvers than hovering. Now that we have an idea how we can actually steer in the air, let's have a look on how we actually figure out where to go. Like, what is the free space? How do we plan our paths? We're using a technology called sparse voxel octree, or SVO for short for this. And I have here a 2D illustration, which is then a sparse voxel quad tree, to explain how this process works. Our starting point is that we have a large grid. In case of the Waterwing, the grid cells are 64 by 64 meters. And in each of these grid cells, we generate one of these SVOs, one of these trees. So let's zoom in into one of these grid cells. The brown mass you can see at the right, that is an obstacle. This is something we cannot traverse and we want to avoid. We start out generating our tree by placing one root node that covers the entire cell. And then we subdivide it, in the case of in 2D, into 4 equal squares. And we can apply multiple subdivision steps until we reach the accuracy that we desire. Then the next step is to go through all the leaf nodes and figure out whether or not they're in free space or whether or not they're occupied. If any kind of geometry is in any of the leaf nodes, then we consider them occupied. It doesn't matter how much of them is covered. Now, you might already notice that we have situations where the entire subtree has the same color. So light blue, in this case, then it's a free node, and dark blue is this is a blocked space. And like the subtree that has the leaf node 1, 2, 3, 4 here, they are all free. And the last subdivision didn't really add any extra information. So we can transfer this information to the parent node and prune all the children that have a parent with fixed information. And this is the sparse part of this voxel tree. So this is, allows us to reduce the memory footprint and of our navigation architecture in places where not much is happening. So one of the neat features of SVO is that in places where there's a lot of free space, which in the air is quite often the case, it actually requires very little space and is very rough and only becomes very precise around areas where you actually care about precision. Now, in order to actually apply pathfinding to this, we don't use the SVO tree directly, but instead we take the leaf nodes and we annotate them with neighborhood relationships to their neighbors. So we find all the leaves, figure out which are all the neighbors, and we represent all the leaves by a node in the center, by a point in the center of this node. And now we also link them to neighboring grid cells if there are any free nodes. And now you have a classical graph that you can use for pathfinding and to figure out if two places are connected, just like you did if you're using an off-mesh or similar architecture. Now you may wonder, how does this transfer to 3D? Because all of these examples were now just 2D. There's actually only a very small difference on how this works in 3D, and that is our grid cells, in this case, are cubes or voxels rather than squares. And at each subdivision step, we subdivide the cube into 8 smaller cubes rather than 4 squares. And this is where the oct part in the name comes from. So this is how we then, following the same procedure, get a sparse voxel octree, or SVO. Here you can see a recording of our debugging tool displaying a path query in SVO. So there are a couple of things to see here. The white voxels you see on the bottom, this is an approximation or a voxelization of the physics that we use to determine whether or not a node in SVO is free or occupied. So since we're generating SVO dynamically at runtime, we prefer to use something cheaper to check than doing constant raycast against the actual physics geometry of the world. And this is what this represents. The blue line that may be a bit difficult to see is the actual path we found in SVO. And the yellow wireframes around this are the nodes in SVO that we expanded to find this path and to follow this path. One of the interesting benefits on SVO is it's a full 3D navigation architecture that allows us also to navigate under bridges and in caves and otherwise enclosed spaces. So this is like different to using height maps or other more 2D inspired architectures. We can deal with being inside something. And this will become more important later. Now, you may wonder, we got these weird zigzag paths from the SVO. They look a little bit funny, and we don't really want to directly follow them. They're often like way more complex than what we actually want. So what we end up doing is we do a post-processing step where we try to straighten them, which is something like string pulling algorithm, to find the longest straight segments we can find along these paths. Again, since a lot of the airspace is relatively open and free, very often we do end up with just one straight segment for the entire path. So the original SVO path mainly serves the purpose to figure out this point is actually reachable, as well as a fallback on situations where we do need to navigate more complex terrain so that we have at least some secure paths we can follow. And in the case of hovering, we often just directly use that straight path and then steer along it. That works for hovering often quite well. We found during the development that especially when it comes to gliding, the results were not that great if we just stick with the straight path. So we have another post-processing step to work further with these paths. So here we again start with this zigzag SVO path. We apply straightening to this and translate it into one straight segment. And if you would now just steer along this path, then we would get a trajectory kind of similar to this orange line. And this one, unfortunately, has two problems. One is the straightened path we have validated against SVO. We know this is free space that we can actually go along. But if we just now rely on the steering, we will overshoot a bit and go into space where we don't know beforehand whether or not it's actually free. And it can happen that you may run into a wall, and then you need to cancel your plan, replan, figure out where to go. And that just doesn't look very smart if your machine happens to very often fly into obstacles and has to stop. So we kind of don't see this very often. The other thing is the steering is relatively aggressive and tries to get to this path as quickly as possible. So it will do very sharp turns, which don't look very natural and are a bit hard to sell. Either you have to reduce the velocity so that we actually can sell that it can do these curves and apply a lot of banking, or it's going to look quite weird, and it's not really also how birds would move. Because if you're flying through the air, you're actually more concerned with maintaining your velocity than taking the shortest possible path to your goal. So you're more likely actually to fly larger arcs because they require less energy and lower acceleration to pursue. So to get closer to this, we apply Bezier smoothing for gliding and sometimes also for hovering, where we take your current forward direction into account, and we then find the distance where we want to place our control point. The distance is based on the angle between the straight path and our forward direction, as well as the length of the straight segment. And then we get this sine curve that you see here that we then can follow along, and we get a much nicer, even path that sells the idea much more that we're like energy efficiently flying through the sky. Now you may wonder what happens if that Bezier curve, that smooth curve, is actually blocked. And this can happen. We have a second fallback step where we try this with a bit tighter curve, closer to the straight path. If that also fails, we're going to do the steering against the straight path. So this Bezier smoothing in the end is more a polish for like the 95% good cases and less of an improvement for the rare problematic cases. So it's mostly a cosmetic improvement that applies in our case quite often. Now we talked quite a lot about flying, and I think you do get a pretty good idea now how this sort of works. So let's have a look at swimming. Similar to how we started, let's get into the water first. So again, we're following roughly the same procedure. We validate the destination, that it's actually in water, that there's enough space actually for us to swim around. It's again animation driven, so we're gonna play a dive animation to get underwater. We'll disable again clamping, because there's not always navigation data structure along the entire path. Then the following step was to switch the movers so that we can use the new mover in the new terrain. And we'll finish in the new navigation space. But hold, there's one thing that is different in this transition. And that is we don't need to switch the mover mid-air. And that is actually pretty much already the secret on how we do the whole underwater swimming. We use SVO and the air mover underwater with very little modification. Because SVO is a full 3D navigation architecture, it can deal with closed spaces. And for us, the underwater world is basically just a canyon with a roof being the water surface. The separation between water and air and separating these two SVO volumes is important for us because most of our flying machines are not allowed to swim, and most of our swimming machines are not allowed to fly. So we don't want them to accidentally pass from one area to the other. So only the Waterwing is actually allowed to transition between these two mediums directly and has a very bespoke action and animation to do so. And then we use the same pathfinding tech, the same post-processing for the path. And the main difference is we're playing a different animation. We're in a different animation state to sell the idea that we're swimming, and we're also reducing the speed because you're supposed to be underwater and there's more resistance than in the air. But in terms of the technology that we use to make the machine move, to figure out where to go, it's exactly the same deal as in the air. And yeah, lastly, for completeness, we get back into the air following the same steps as we got into the water. Now this wraps up the first part of this presentation, where I gave you an introduction to the medium transitions we have, going from the ground into the air, into the water, and back. I talked about the two different movement modes of hovering and gliding, which we use in the air and underwater as well. And I gave a primer on generating SVO and using it for pathfinding and the smoothing and the post-processing steps we apply afterwards. If you're putting all of these things together, you can build the idle behavior of the Waterwing, which mostly serves for lore and world building, because our machines fill a certain role in the ecosystem. So it grabbed some resources from the ground and is now flying along the coast to find a good spot to distribute them. We'll here stop a little bit in the air and play a gesture to give the player a better chance to actually observe this behavior and see the diving. And then underwater, we start a particle effect to deliver this algae bloom, which then also attracts local fish life, which is also just particle effects. Now, in our game, you spend a lot less time just observing the machines, as fascinating as this might be, and much more time fighting them, either because they're an obstacle for your quest of where you're trying to get right now, or because you're deliberately hunting them for their resources. So let's have a look on how this looks like. We have at the very core, we have a relatively simple combat loop for our machines, which starts with intercept. This is basically just a fancy word for I'm running into your face and trying to get as close as possible. And while we're doing this, we're constantly evaluating if we have any attack available that we can use right in this situation. One of the main criteria for this is this attack in range? And for this, we use trigger volumes, which you can see here annotated in green, which is a geometric shape relative to the machine that tells us if my target, my threat is in sight, then we know, okay, now we can use this attack. And sometimes we might end up very close to our enemy without actually having any attack available for whatever reason. And in these cases, we'll play an evasive maneuver to gain some distance so we can repeat this loop. The actual combat behavior of our machines in the game is more complex than that, but it does still build on this core loop on top, and everything is additive built on top of it. Now for the Waterwing, melee attacks play a big role. In order to make melee attacks work, one core tech is warping. Warping allows us to play an animation and vary the distance you travel during this animation at runtime. So here you can see one attack played at 2 different distances against the target. And here you have a direct comparison between the distance traveled between these animations. And we're using the exact same animation for this attack in this case, because it would be from workload not really feasible to animate all variable distances on which you may want to use the attack. Assuming that not every one of you is familiar with how warping works, I have prepared a primer. And here in this stylized view, at the bottom, the 10 arrows represent our animation frames. So each arrow is 1 frame of the animation. So in this animation, we're expecting to hit our target at frame 9, which is the target frame. And the length of the arrows also indicate on how far do we travel in this animation frame. So if our target happens to be exactly at the animated distance, then we can just play that animation and yay, we hit our target, perfect. But more often than not, the enemy we're targeting might be a little bit further away or sometimes even a bit closer. And if we would just play the animation unaltered, we'll miss and give them a large opportunity to retaliate, which doesn't really feel good and makes the game a bit too easy. So during the first couple of frames that I annotated here with update target, frame 1 to 4, we constantly monitor where our target is and how far they moved. And we'll compute how much more or less do we need to travel in order to actually reach that position, which are now here marked in the blue bar. So this is the extra distance we need to travel if you want to reach that target. Now, if you would just add this extra travel distance between frame 8 and 9, that would just look like a glitch, and you basically teleport, and it's also super unfair to the player, and just looks broken. So we need to obscure a little bit that we're actually traveling some extra distance. And to that end, we're doing 2 steps. One is we split the extra distance over multiple frames. And the frames we're allowed to do this, we mark them as displacement. Those are usually the frames where most of the traveling happens on this attack. So this is where we have most of the movement. And preferably, if the animation allows it, we use frames in which we don't have any ground contact. So where our machine is jumping in some kind of form, because then it's less obvious that we're tinkering with the velocity and make it actually move faster than animated. So we don't get any visible foot sliding. And if we now just play the animation with the extra movement, we again reach our targets and our robot is happy. Now, here you see a clip on what our combat can look like underwater. You see the water one executing 2 attacks. Underwater is in Horizon Forbidden West the only place where we're actually fighting in a full 3D environment, as this is the only place where the player can move in full 3D. The other situation that is special about this is the player cannot fight back underwater. So this is not really an even fight in any way. And therefore, we actually put a lot less effort to be very effective, and we have a very limited set of attacks here, because all we really want to do is we want to scare the player away and threaten them, so to make them retreat, because that's literally the only option they have. Or we stealth. There are some options to stealth in the water. When we're in the air, the situation is a little bit different. Since the player controls a human, Aloy, they will spend most of their time on the ground while our machine is flying. And while many of our machines in the air prefer ranged attacks to combat the player, the Waterwing really wants to get close and really wants to sell this aggressive, very melee-focused idea. So what we want to do is we want to get down to the player as quickly as possible. And we ended up combining a landing with an attack for this purpose. So this scene basically uses almost all components shown in this presentation, from hovering through the air to position ourselves so that the trigger volume contains the player, then playing a landing that does all the validation steps, etc., and switching movers during the animation, as well as doing warping for the attack to get to the player. And as a result, we can do a very threatening maneuver and at the same time land and keep the pressure on the player. And that's it for part 2. You have seen how some parts that we use to get this relentless melee attacks for the Waterwing, starting with the basic attack behavior loop that we have, the primer on how we use trigger volumes and warping for those. And I briefly discussed some applications of melee attacks underwater and for landing. All of this is, of course, a team effort, and those are the folks at Guerrilla I'm working together with on building these behaviors and the tools necessary for this. And also, Alo gets some teamwork to get rid of the glint hog that snuck into the presentation. Thanks for your attention.